All right, hello guys. So the topic this week really is sort of uh, spectrum of topics actually. So it's not a singular little topic. Um, but if you want to look for a really overriding theme, it's really about recreational mathematics. Okay. And it's not actually as flippant as it sounds. This isn't something that's sort of brushed off as a non-serious mathematics. This is still many of things are very serious mathematical lines of inquiry. It's just more of a playground where the access is much quicker. You don't have to become a seasoned expert with years of study to kind of enter into these sort of things and play around. Certainly to make insights or to explain insights, the more experience you have, the better. But that doesn't mean that that you can't make interesting progress with very little expertise. All right, so that does bring into, so it comes down to then, okay, what are the things that you can explore with or sort of experiment with without being an expert? Well, they come in a variety of things, but the emphasis I want to have, and I think looking over what I can share with you and what we've been working on, is it's really mostly about a few things. So one-dimensional, so 1D, one-dimensional. Oops. Objects, right, that V started becoming a J as well. One-dimensional objects in 3 dimensions. Okay, silly as this sounds, this is something we mess with a lot, right? So think of a string in the ambient space in which we live. I'll also talk briefly today about 4 dimensions. Okay, what kinds of things could you do with a one-dimensional string in 3 dimensions, in 4 dimensions, I mean. Right, and then take up where it can actually get pretty complicated, 2-dimensional. Objects, and I'm probably not going to get into any too much four-dimensional stuff, but again, I'll mention a few things where we might need 4 dimensions to do certain things. All right, one-dimensional objects, I'm going to kind of stick to things called knots. Okay, I'll explain what the definition there is. All right, for 2-dimensional objects, these are usually referred to as surfaces. There are some other things that could fall in this category. So one-dimensional objects in 3D or in 2 dimensions or in 4 dimensions, these are often also called curves, especially if they're don't have a closing point. Some fancy words that you might start seeing if you start studying 2-dimensional objects. Some of the words might be 2-dimensional 2D manifolds. All right, so manifolds are things that look like Euclidean space up close, but they may have some curvature or something that makes them not straight, not Euclidean anymore. Okay, so I have lots of examples of these things here. All right, so let me start with what is a knot. Okay, so what is a knot? Well, the best definition I can based on the knowledge you likely have. So a knot, K-N-O-T, is in embedding. So I'll need to explain this word. Sorry, my preference is to list out the sentence and then expand on any words that you may not be familiar with. It's an embedding of a loop. I want to give you a definition of what I mean by a loop as well, so I'll drawing that as a to-do list. So a knot is an embedding of a loop in 3-dimensional space. So the common notation for that is R3. Okay, so that's if I'm drawing a coordinate, when you draw a coordinate plane, you draw a coordinate space for this. You have 3 axes, an x, y, and a z. All right, so an embedding So this is a one-to-one map, meaning 2 points are not mapped together, so there's no overlap or crisscrossing. So it's a one-to-one map, and needs to be continuous. You should be learning what continuity is or have learned. So it's a one-to-one map that is continuous. On occasion, there will be people that insist when they use the word map, they insist on continuity or something. But anyway, I'll note that it's continuous. Right, a loop is a specific sort of mathematical structure. So it's easy to draw. I'll draw mine as having some sort of base point. I like this because it is combinatorially useful, but too common as more than one sitting here, but I have 2 knots with me. One is made out of paracord, and one is made out of some flat wire, and both of them have a weld or a seal shut. So here's where I took a lighter and melted my paracord shut. And then on here, not that you can probably see it on the camera, but there is a weld, here it is, a weld where the flat wire is welded onto itself. So how did we get there? Well, you can take the unit interval, which structurally looks like this. Right? There's a point you can call 0 and a point you can call 1, and then there's a string of points there. And what we do is we say, okay, we want to glue these points together, so we do something fairly interesting to create an equivalence. Right? And this is kind of one of those places where someone who's not a mathematician can say, okay, this is where mathematicians just start playing around and doing silly things. Maybe I shouldn't use the symbol equality. Okay, so maybe what I'll do is I say 0 is equivalent to 1. Use a different symbol. Maybe that's less offensive and less confusing. But both of these are going to mean the same thing. And what I'm doing is I'm taking this set and I'm declaring that 0 and 1 are going to be the same point. And so what I end up with is this. 0 is equivalent to 1. Okay, and then I have the rest of the unit interval there. Okay, so take a breath for a second. As weird as this sounds, this is not an uncommon procedure in mathematics. We do this quite a lot. Some places where you've seen this before. As you know that for practical purposes, 2/4 is equal to 1/2. The equality there is somehow some algebraic equality here, right? The way this numerically works out, right? But then there are ways of thinking about these as slightly different fractions, but they're the same rational number. Okay, and the reason why you might think of this as a different fraction is this is the fourths is dividing things into 4 pieces, and you're selecting 2 of them, and here you're dividing things into 2 pieces and selecting 1 of them. In the end, you selected the same amount, but the division and unit selection is not the same in each case. All right, where's another place that you might have seen this? Well, one thing I've sort of instructed your mentors is to give you some places where you can play around, and this sort of gluing together is often done on many sorts of video games you might play. Okay, so I'll get to that when I start talking about a torus, but keep in mind this is not an uncommon video game trick. All right, I just need to preserve my room so I can give you some ideas, some knots here, and then I'll explain some of those things in sort of this next video that we're having clean board. All right, so back to a knot. All right, so there are some things that are not knots. So fortunate, use the English language here. All right, so let's see if I can do this without. I promise. Let's see. So I always have to do that. I always want to feel like someday I'm going to be able to do this without erasing part of it here. Okay, so this is a common overhand knot, how you tie your shoelaces in some cases, or you. So we use the word knot quite broadly in the common everyday sense. The place where this fails to be a mathematical knot is the ends aren't glued together. So how do I fix that? Well, something that is a knot. I can talk about this thing, but what I need to do is I need to glue the ends together before I have a proper knot. Otherwise, you can untie it. All right. Anything you can untie is probably not a mathematical knot. The way to fix this so you don't have the ability to untie it, you got to seal your ends together. So to turn this into a mathematical knot, again, I feel like now that I have a copy in front of me, I think I can do this. Look at that. Ta-da. All right. So there we go. Okay, of course the gap means the curve is going over, and the sort of the missing part is the part of the string, if you will, that's going under. Right, you can maybe do this with dot, 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 or something, some other feature, or you can use maybe some sort of, some other notation, if you like, about how to follow which one's on top. Okay, there's a lot of material in knot theory, so I don't want to claim that I'm giving you some profound amount of knowledge to deal with knot theory, but you should start getting a feel for what is a knot and what is not a knot. You need the ends sealed together. As soon as you have a loop that has the ends sealed together, you have a knot. All right, these two knots are different, all right, but how do you tell if they're different? And that is not the easiest thing to do. Okay, but there are some rules. So first of all, we do have to note that this is a knot, and in fact, its name is fairly special. It's referred to as the unknot. Okay. I'm sure that was intentionally as humorous as it sounds. The one that seems to have no knotting seems to be the one called the unknot. All right, this one cannot be untied to form that one because the ends are sealed. It's particularly important. All right, but the reasons why you can't move this one into that one, that takes some mathematical work, right? So there are some interesting techniques in, we can say, coloring the strands. There's some neat things. I don't think it'll take you long. If you just Google, say, knot theory and watch some videos on YouTube, you'll start seeing some interesting techniques about how to tell knots apart. But oftentimes the technique will fail when you compare certain knots that are definitely different, but the technique can't discriminate between the two knots. Okay, so why knots? Well, they're fairly easy to get into because you already have some passing familiarity with tying knots yourself if you've ever tied your shoes. The one part that's missing is the ends of your shoelaces need to be sealed together before you have a knot. All right. Secondly, I mean, they're tactile, right? Not in that way, and these are what I mean by one-dimensional objects in 3 dimensions. It's easy to get into studying them. The techniques get very sophisticated very fast. But let me show you 3 knots I have with me. So these two are the same type of knot. In fact, actually all 3 of these are the same type of knot. They fall into a class of knots called toral knots. It turns out this knot is also a toral knot. Now, not all knots are toral knots. It just so happens the examples I have here are. There are plenty that are not toral knots. Again, this is something you're probably going to have to explore if you want to see what knots are not toral knots and which ones are. But these are all toral knots of slightly different sorts. All right, and one reason why I like doing these with students is I'm not saying all of you have done this, but a lot of you probably have. I know I did as a kid. Is if you take willows or anything or grass or whatever, you can actually go and make these. Just the ends aren't sealed together. The ends are somewhat loose. You can actually make these, and you can make crowns and bracelets and things with them. So they're easy to make in that way. You just kind of spin it around and keep going like that. But mathematically, they're quite interesting. And in fact, it turns out they're quite a bit more interesting than you would expect. This is also a toral knot. It's made with this flat wire, so it has some tension in there. And what's neat is toral knots actually can be turned into two orientations. Right now, you can see it has this, what you call maybe this major rotation, and then this minor rotation that goes around its major rotation. But that role can be almost flipped. So if you let it go, all of a sudden now, it's still actually technically in that orientation. You can see it's fighting against and trying to bounce to the other one, where the two major and minor rotations are flipped. Now, of course, it gets in its own way, which is typical of knots to get in their own way when they want to switch from one thing to another. But it creates this neat thing here. This is a toy I got at a toy store. I think it's usually these things are called kinetic springs or something like that. Name doesn't make any particular sense to me. But when I saw it, I said, okay, that is the best toral knot I've seen at a toy store. And you can do that. And of course, what's neat is the thing will roll like this. Okay. This is a neat feature of how this knot lives on this surface. There's a thing that this surface can do that a sphere cannot. Okay. All right, but just strings living on this sphere. You actually, if you think about it, try to think about putting a loop on the sphere in a knotted way. I can invite you to give that a shot. Start thinking about how to do that. The thing you can't do is, remember, if it's going to be an embedding, the knot can't cross over itself. And so it's pretty constrained to what can be done with it. So you can think about trying to draw a loop on the sphere in such a way that it's a knot. I encourage you to think, can you actually make anything besides the unknot in that way? All right. Okay, so what do I have with me that we're going to talk about in sort of this next part 2 of this video here? I have other things with me besides just strings, all right, besides these toral knots. I'll bring up these toral knots again when I start talking about surfaces. Clearly I have the styrofoam surface for a reason here, and that's part of it. It's also where I'm going to bring in the video game chunk to think about why toral knots are interesting in that way. All right, so I'm going to get the board clean, and then I'll see you on the next video. All right, let's move on to surfaces, but don't lose track of the curves and knots. All right, they're a good model for how we're going to build surfaces. And what I want you to keep in mind is there's kind of 2 features of surface. There's sort of its intrinsic structure, and then there are pieces of geometric tidbits, okay? So, one of my hobbies, as I mentioned, was crocheting and knitting, and this one I did crochet because crocheting is much faster, is I made sort of 3 objects, all right? And the way I have them made, notice in particular there's a hole up here that's pretty important. They're all essentially the same structural object, but they have different geometrical features. Okay, so this one, this doily, this looks like would hold. You could put a cold drink on it. It's flat. All right, so it has some interesting ways of looking at it, and I think this is the best way. This is my favorite way of understanding it. Is there's a number of stitches that go around. Sort of like the circumference. And if I take a ratio of its circumference with either its radius or diameter, this particular case, I should get a very old friend. I should get something involving pi. If you're doing radius, you'll get 2 pi. Okay. So you can think about this actually as a geometric feature of flatness, is that you get 2 pi. All right, now, this equality is actually a boundary line between what if I had a circumference and I get greater than 2 pi, or if I had a circumference, divide by the radius, I make it less than 2 pi. Okay, so if I'm intentionally trying to crochet one of these doilies things, I actually either need to have one of two things. I need to have a pattern that's done this for me, told me how many stitches to go around. Or if I know math, I don't have to have a pattern. I just need to know that I need to keep my ratio close to 2 pi as long as I know how tall and how wide my stitches are. And you can do that by making yourself a square sample. You can tell how tall they are and how wide your stitches are. Just measure with the ruler. All right. So I have copies of these, and you do have to kind of use your imagination here because I've done two things with this to make a sphere. I've kind of gone out and then I've contracted back in. So think about is just excising this at the equator and think about this being a bowl. Okay, and this one's good. This one I didn't have to do anything, do anything to it. You can see it's really, really wiggly at the edges. It's like coral. A lot of biological organisms of various sorts, right, from very, very primitive to quite complex, have this, right? Our brains are actually in this structure, and coral grows in this structure, and you can see they're very different things. I mean, lots of other things grow this way. All right, so if you take a look at this one, mark it down for me, mark all over it. I've actually done the same thing in both of these, but what got out of hand was how many stitches I was using to go around. So here I was very careful to only add stitches as needed, but here I added a ton more. And in fact, I think I was adding 2 stitches on top of every one below it. So I was doubling the stitches every time. And so that became this particular thing. The circumference really started to exceed my radius. It got bigger and bigger faster, so it got way greater than 2 pi. Okay, so these all actually have names. This is usually referred to as either flat or Euclidean. There's one thing you should get away from in the FYE course is be able to say Euclid and Euler. They're pronounced differently. So Euler's not Euler, it's Euler. Sorry, just putting that out there. Euclid is Euclid, Euler is Euler. Okay, don't say Euler. All right, this one, this wiggly one, this is where the circumference got quite a bit bigger, and this is referred to as hyperbolic. And the curvature is actually negative. All right, this looks like how a Pringle chip is shaped, except this is an extreme version of a Pringle chip. Pringle chips have negative curvature. All right, before I get drop my Euclidean surface here, if you just take half of this, things like a winter hat, you have this thing, right? The circumference actually isn't quite long enough to make a flat surface. It's actually a little too short, and so you end up with this. And this is often called parabolic, like a paraboloid, like a parabola, but two dimensions there. Parabolic, and this is positive curvature. I should say curvature here. Okay, not going to be tested on any of this that's in these videos, so don't feel like if you feel like this is going in one ear, not the other, that's sort of okay. This is here as a reference to kind of look back at and digest what you can from it. Okay, this is a good detection tool for figuring out if you're on a flat surface, a hyperbolic surface, or a parabolic surface. So if you're interested in the geometry of the surface, this is how you detect curvature. Plenty of other mechanisms. It gets very complicated if you want fine measures of curvature, right? You want a number. You're going to have to work pretty hard to get there. But these tools alone will get you at least to detecting zero curvature, negative curvature, positive curvature. Okay, so use the circumference radius. I call it sort of the take your dog for a walk test. So put your dog on a leash, let it make a lap around you. Right? If it's 2 pi tired, then you're on flat. If your dog is much more tired than you expect, then you took your dog walking in a hyperbolic surface. If it seems like your dog's not as tired as you need, you took them on a parabolic surface. They didn't walk as far. Okay, so it's like taking them walking in a bowl. They don't have to walk as far. All right, so what I want to do is keep in mind we're not always going to be able to follow the geometry on there. But sometimes we can make some comments about the geometry. What I want to segue into is structure. So just the structure of the surface. So I have geometrically very different versions of spheres here. So here's a kind of a, if you excuse the dents in the styrofoam over the years, that's a pretty round, smooth sphere. The curvature here is equal everywhere. It's positive curvature, in fact. These two I use in combinatorics classes, and they actually don't have smooth curvature. They actually have flat places, places where it's flat, and then these sort of vertices here. There are ways to interpret how the curvature is condensed at these spots, and you can work with calculations that say how, what's its contribution. But there are places where the idea of curvature doesn't make sense. There's actually like a lack of differentiability in the surface, right? If you're taking calculus or have taken calculus, you should be at that point to realize that sort of these points in the curves are places where it fails differentiable. Well, here you go. These surfaces here have points where they actually don't have a defined curvature in terms of the sort of differential perspective. Okay, there are combinatorial ways to get around it, but here they have that. So structurally, when it comes to structure called the topology, these two surfaces are the same as with this one here. Okay. Granted, this has color and other faces. This one was made by a student in the combinatorics class. I felt to keep it. It's a dodecahedron. It's really cool. So I have three spheres here, right? Geometrically have different sort of things going on, but structurally, topologically, they're the same. Okay. Now I have some other surfaces here that are apparently quite different. And here this should look like a barbell. I can actually inflate this into a perfect, more of a torus, what looks like a donut, but I like the barbell. It's a good sort of segue in between my coffee cup, which has tea in it at the moment, usually has coffee. Right, the difference here is, if you look it up, they both have handles, but this has the sort of the spot for the tea, and this does not. So all you have to do that is to take this and kind of smush this in, right? But if you're going this way, if you're going from coffee cup to this bulbous thing, the only thing you have to do to get to here, is using the rope, is kind of just smooth out the handle so that the bulbous part isn't quite so dominant and it's even all the way around. Okay? So this process of deformation is usually referred to things like homotopy or isotopy. The word tope, T-O-P, again referring to structure. So these surfaces are all structurally the same surface, but again, geometrically are different, right? They have different sorts of curvature. Sometimes you see gluing points that are not differentiable. This balloon has this goofy knot here. I'm not sure if you want to include that part of the surface or not. Right, so geometrically different, topologically the same. Okay, I can actually go back to here. I made topologically the same structures here with my yarn. Even with this one, all I have to do to get from this one to this one is if it was stretchy yarn, I could take this hole and flatten it out. Okay, it has that hole in it. If I was to close it up, all of a sudden now I'd have something topologically different. But as of now, this thing is just a disc that's trying to be a sphere, but it fails, right? It's not quite there. It has not completed its process of becoming a sphere. Okay, maybe that's sad or funny. I don't know. But so there you go. Okay, so these are concepts that are really important, especially in more advanced math classes. You don't get to play with them in calculus that much, but we got these surfaces. Okay, so a sphere is not super interesting, but this torus and some other cousin surfaces are incredibly interesting, and this is where I want to bring back the video games and toral knots. Okay, so the first thing, this is an actual homework assignment that you should do. You won't get any grades for it or anything, but what I'm saying is an activity I really would like you to do is find a free copy of Asteroids. It's been around forever. It's an old video game. And the game is played on a square screen. Could be your computer screen or a little applet window of some sort. And when you fly off the screen, you return back on the screen, but not where you left. So if I went off the screen this way, I would return over here, like that, and continue on. And same thing if I flew off the bottom of the screen, I would return to the top, following my same trajectory like that. All right. So what's actually being made here is this is not played on the surface of a sphere. It's not played on a square either. It's actually played on the surface of a torus. And what that looks like is the following. So it looks like this. I'm going to draw some sort of intermediates too, but I kind of want to give you the answer before I try to lead you there. My glue lines here, we call this A and A because these two are going to be the same, and B and B. Do you remember when we did in the last one, when we took the unit interval and turned it into a loop by saying 0 and 1, we're going to call the same thing. Okay? We're doing the same thing here, but now with, instead of unit interval, we're doing it with a unit square, or just a square. So opposite sides get glued together. So if you just do one pair of opposite sides without doing the other, you get a tube, right? So I could have something in an intermediate surface like this. And here's my glue line. Here's where my A's were glued together. And then my B edges just are not glued together yet. So if I glue them together, what I end up with is this. And I'll use dotted lines, so it's... Okay, so maybe A was this sort of major glue line, and then B was the caps together. Okay. You can, if you actually reverse the order of making the tube, doing a B and A, you end up with sort of like a different version of the torus, but it's still a torus. Okay. All right, and then these trajectories passed over B look much simpler. So here's my B1. It looks more or less just like this. No break, no this warp from the top to the bottom. You're just going right over that line. And over A, it looks something just like this, right? You're just passing right over the line. Right, so this is sort of a copy of the same picture. It's just hard to make a screen in this shape and ask people to envision it. If you use the square format, much more straightforward. Okay, so why is this important? Well, this build-up from taking a simple object to build interesting objects is incredibly important. In fact, there's plenty of unsolved math problems that require this sort of build-up. In addition, toral knots are actually really nice to understand on a square model. They look like a wound-up piece of gobbledygook that's difficult to classify in this context. But if you take the square model of the torus, as opposed to this model that has, this actually has no curvature the way it's surviving here as a disk. This actually does have curvature, but it doesn't have the same curvature everywhere. On the inside, it has Pringle-like curvature, has negative curvature on the inside. On the exterior, it actually has positive curvature, like a hat. In total, it actually has zero curvature. If you add up all the curvature, but locally it has either some negative and some positive. Right. But here it's completely flat. So this is often called the flat or Euclidean torus, if that makes any sense. Once you start bending and folding, you start introducing curvature into it. And this is one reason why this is very hard to do with paper. You can make the tube with paper. Turns out that is still has what's called curvature, zero curvature. Tube actually has zero curvature, but you can't bend the tube. As soon as you bend the tube, you start introducing curvature. Okay, back to the toral knot here. So, if you remember, the one important thing about a knot is the ends have to be glued together. So let me do this with a different color. So suppose I'm playing the game Asteroids, and I flew off the top, turned on the bottom, came back. Came off the bottom, and oh, there. So that means I have to return over here. And I keep flying off and going, right? Until eventually it seems like, okay, let me cheat a little bit and reunite. Okay, there's kind of two possibilities. Either I keep doing this and I don't link up with my previous orbit, which means I won't have a knot, or I do. And if I link up with my previous orbit, I will have formed a knot on the surface of the torus. And that's why these are called toral knots. There is a matching between the slope of this line and the different toral knots you get. So if you think about this being a unit square with actual, values in here, and you think about the slope of your line, right, as rise over run, this is the neat thing. Rational slopes give rise to knots because they come back to where they started, and these things are often, the name for these are toral knots. From like a dynamical systems perspective, this is going to give you periodic orbits, right? If you come back to where you start, you'll just continue on. But from a knot theory perspective, this is a really neat thing. This gives us a rational number that we can associate with our knot. All right. And so the overhand knot is like a 3-2 toral knot, and there's other versions of that. So, okay, so definitely play the game Asteroids, get a feel for this. Okay, this is only one way of many in which you can glue together the square. Alright, if you're familiar with making a Mobius strip, and you should if you've watched the other videos that I posted today, right, you just have to glue together a strip of paper with a twist. You can definitely twist here, right? So instead of gluing this together without a twist, you can start introducing twists. Alright, and this is, let me just put this as a note, if you start introducing twists when you glue these as opposed to gluing them without twists, you end up with things called, Klein bottles are possible. That's if you have one twist one way but not the other, right? So it might actually be, it's typically thought of as easier to make the tube first, the untwisted connection first, and then if I'm going to connect the B to the B, I have to do it with a twist, which means I have to actually come through the other side. And that's how you end up with this Klein bottle shape. Okay, so this is gluing but with twists. So this is one twist. And then this other thing called projective space. Okay, it has other names too. This is just the most common one, and that's two twists. So that's a twist with each gluing. So the A to A gets a twist, and the B to B gets a twist. All right, Klein bottles and projective spaces actually can't exist in three dimensions with an embedding. You actually need a fourth dimension to pull this off. Otherwise, you can't embed them without points kind of collapsing into each other. You get these self-intersections. So if you start looking up what Klein bottles are, they're bottles that actually only have one side. Right? Normally, you think of a bottle having an inside and outside. Klein bottles have no inside and outside. They just have either what you'd call the inside or what you'd call the outside. They're super interesting. Projective spaces could be made in the same way, but they're slightly more complicated to pull off. And I'm not sure if they're quite as much fun as Klein bottles when it comes to making things out of glass. But these are worth looking up and starting to learn a little about if you're curious. Okay, so some takeaways here is there's a lot of ways to play games with just gluing things together. Okay, the two basic things we glued together today have been a single piece of string, right, an interval, glue the ends together. The other thing we did is took a square and glued opposite edges together. Okay, I had you start last week gluing together paper, right, strips of paper with actually a number of twists and folds. Turns out, you're just doing something here. It's not exactly like this. You're actually creating a slightly different sort of object, right, with these hexaflexagons. But again, you're gluing together simple objects to form something mathematically interesting. And it turns out it's some sort of actual Mobius strip is what you're making. It's in that class of objects anyway, not a simple Mobius strip, much more complicated one. But I have made a hexaflexagon with different colors here with cardstock, and it's quite massive. And so I have the corners cut off so it flexes a little better. You may want to do the same thing if you're interested, so you get lots of colors there. So you can color yours too. I would recommend a colored pencil if it's just a one-sided version. There are certain things you can do on a torus that you can't do on a sphere, and here's a project a student made. They put a specific graph that normally would intersect on a sphere, but you can draw things on a torus that you can't draw on a sphere without intersections. So there's lots of fun games you can sort of play and things you can do with just these simple little building blocks here. All right, so questions you have or interesting directions you might be interested in learning a little more, you should let let myself and your mentor know. We can help you, help guide you where those resources might be. There's a lot of playgrounds of things to play with. Now I've kind of opened a lot of doors to say, hey, look in here, look in here, look in here. I'm not expecting you to sort of learn all these little things. This is a lot to take in, but hopefully you find something you find at least piques your interest a little bit. Okay, so again, hopefully you have a good week with your mentor. Hopefully you can successfully get your hexaflexagon made. Probably a trihexaflexagon, but if you're feeling ambitious, I would encourage you to try out the hexaflexagon. Its states are a great deal more interesting to play with than the tri version. So give that a shot if you're able and willing. All right, so I'll see y'all next week.